let us delineate the roles of these internal and external damping terms. So, let us see how they are actually a little different. So, for this let us consider. So, we are going to look at the difference in roles of this internal and external damping. So, to understand this, let us consider this simple example of a fixed bar in axial vibration. So, the equation of motion is this. The boundary conditions are given by this. So, therefore, I can expand as you know that these are the eigenfunctions of this fixed bar. So, when you substitute this expansion and take inner product, so we substitute this expansion in the solution and take inner product with sin k pi x over L, and that filters out the kth coefficient in the expansion. So, what we are going to get so this term is for the external damping, this term is for the internal. So, this external, this is the internal damping, and so this is what we are going to get. Now, let us look at this equation one by one. So, suppose there is no internal damping. In that case, so when we have only external damping, I can write this as which can be written as and if you compare then zeta k can be written as this. So, you see that this k appears in the denominator of this damping factor. So, which means that for high values of k, this damping factor actually is very low, which tells us that external damping is not inefficient in damping out higher modes. So, higher modes are damped less compared to the lower modes. We will look at the reason for this. Now, let us consider the internal damping case. So, in that case I can write and once again if you represent this term as 2 zeta k omega k, then now you see that k appears in the numerator. Therefore, for higher modes, higher values of k, zeta k is high, goes higher. So, which means higher modes have better damping because of internal dissipation. So, internal damping is more effective for higher modes, while external damping is more effective for lower modes. So, external damping is effective for lower modes. While internal damping is effective for higher modes. Now, to understand this, you have to look at the expression of say for example, the internal damping. So, we have seen already that this internal damping, the way we have introduced, so it is strain rate, dependent on strain rate. Now, as you go to higher modes and if you consider the solution, then del u del x. So, rate of change of del u del x, rate of change of del u del x with time. So, if you see this solution is, say for example, for this bar, so you have terms in the expansion of u like this. So, del u del x, so so higher the value of k, higher is the contribution from this strain term at the strain rate term. So, for this reason, higher the mode, higher will be the effectiveness of the internal damping. On the other hand, if you consider this external damping, if you look at, say for example, the first mode. So, the first mode of the bar or the string looks like this, the second mode looks like this, the third mode looks like this. So, higher the mode, more will be the nodes, and therefore, the effective motion of the system in the ambient fluid will be lesser and lesser. So, the effective damping because of external damping reduces as you go to higher modes. Now, let us look at discrete damping. Now, as I have already mentioned, this discrete damping occurs when we attach, for example, an external dashpot to a continuous system at a particular point. Say for example, Stockbridge damper is typically used in high tension cables. So, that is attached to a particular point on the cable, and that damps the vibrational energy of the high tension cables. So, this is a discrete damping or a lumped damping. Other than that, you can have lump damping when you have connections or joints. Say for example, you have riveted connections between two structural elements. In that case, damping is localized at the connection or at the joint. So, for such cases, what you have is the discrete damping. So, let us look at an example. So, this is a bar in axial motion, and here we have a dashpot attached to this end of the bar. So, I can write the boundary conditions of this problem. So, this is a fixed end, and at this end I have the force because of this damper. The equation of motion is like this. Let us search a solution of the form like this. So, we have a discrete damper at this end, and we have introduced this damping not in the equation, but in the boundary condition, which we can always do. Now, once you have once you substitute this solution form in the equation of motion, we obtain an eigenvalue problem. You obtain this eigenvalue problem, and the solution of this eigenvalue problem can be written in this form. And when we use the boundary conditions, so these two boundary conditions can be written in this form, where gamma, this gamma is S times L over C, and this A here, this small c is of course the speed of axial waves in the bar. So, we have to solve this system. The solution for non-trivial solutions of B and C, so for non-trivial solutions of B and C, the determinant of this matrix must be 0, which leads us to as you can very easily find out that this is the equation, which is the characteristic equation. And which can be solved for gamma when A is not equal to 1. When A is equals to 1, there is so this can be solved when A is not equal to 1. If A is equals to 1, which implies that the damping, so the adjustable parameter is the damping, there are no eigenvalues. There are no eigenvalues for this problem when the damping is tuned to this value. Now, so no eigenvalues would imply there are no solutions. Now, but then we have considered solutions of this very special form. So, there are no solutions of this very special form, but then there are solutions which we have to understand in terms of wave propagation. Now, that we will keep for a later discussion. Right now, let us solve when A is not equal to 1, and for solving that we can consider gamma to be a complex number of this form, and then so alpha plus I beta. So, alpha can be easily solved as log natural of and beta is indexed now, the phase So, there are infinitely many values of beta which are now indexed with k, and for various ranges of values of a, we have these solutions. And you can check, if you put d as 0, then you can get the eigen values of a fixed free bar. And if you put d as infinity, then it is a fixed bar. And that can be checked from these solutions that of gamma that we have obtained. Now, here in this slide I have plotted the variation of alpha and beta. So, the solutions of gamma, the real part and the imaginary part, as a varies. So, when a is 0, we have a solution here. So, a will be 0 when the damping is 0, which means it is a fixed free bar, while a is infinity when d is infinity. So, this is a fixed bar, and when a goes to 1, this goes to infinity, as we have already seen, and when a so this is the locus of the solution as a varies. So, as you can see that all modes have the same decay rate, as alpha does not change or does not depend on k. So, all modes will have the same decay rate, and there is a jump from this value to this value as a crosses 1. So, we have considered one case of a bar with boundary damping. Let us look at another example of a string. With a concentrated damper or a lump damper at x equal to a. So, in this case you can write down the equation in this form, and if you use the modal expansion, substitute in the equation and take inner product with the jth eigenfunction, you obtain this. Now, if you consider that this j times a over L is not an integer. So, if you can adjust this a such that this is not an integer for all j, then you will find that all modes are damped, whereas if this does not happen, then some of the modes will not be damped. So, for this situation, when this is not an integer, what we have is known as pervasive damping. So, when the damping is pervasive, all modes will be damped, whereas if you put this damper at the middle of the string, you will find that the second mode is never damped. So, the second mode, the fourth mode, these modes will not be damped. So, the damping is then non pervasive. So, in today's lecture what we have studied is this, we have introduced the damping and we have seen two forms of damping, internal and external. We have studied distributed damping and lumped or concentrated damping, and we have delineated the effects of internal and external damping. So, with that we conclude this lecture.